The differentiation of an integral. This is very important lemma. If f is integrable on closed interval ab, then the function capital F, that is defined by fx equal to the integration from a to x ft dt. This is a continuous function of bounded variation on closed interval ab. So it is given that this f is integrable on closed interval ab, and we have to show that if this is integrable on closed interval ab, then this capital F, first we need to show that this is continuous on closed interval ab, and then we need to show that it is of bounded variation, right? Continuous function and also the bounded variation on closed interval ab. So first we are going to show that the capital F is continuous on this closed interval AB. So this is your closed interval AB, and I'm going to consider the point C belonging to this interval. So let's take a point C that belongs to the closed interval AB. Then if I need to take the mod of f of x minus f of c, because I need to show that this capital F is continuous on this closed interval, for that first I'm going to show that this is continuous on this point C belonging to this interval. So for that I have taken the mod of fx minus fc. So this is equal to, by the definition, what is f of x? It is the integration from a to x ft dt, right? So let's use this, the integration from a to x ft dt. Similarly, writing what is f of c, it becomes the integration from a to c ft dt. On whatever point the function is depending, we are going to take that point to be the upper limit, right? And this a, it is the end point of this interval. We can write this further as, this is a to x ft dt. I want this sign to be changed to positive. So for that we need to shift the limits. So this becomes now from c to a ft dt, right? And now writing this integral first in the next step, this is c to a ft dt plus a to x ft dt, so that I can merge these two integrals to get the integration from the limits. This is from c to a and then from a to x. So I'm merging these two and writing this to be as from c to x. And this mod is further less than equal to the integration from c to x mod of ft dt. So we have got that mod of f of x minus f of c is less than equal to the integration from c to x ft dt, the mod of ft dt. For continuity, we need to show this mod to be strictly less than epsilon, right? For that we need to consider, if we know that this f is bounded, then our work is done. So this f can be bounded and this cannot be bounded. It can be bounded, it cannot be bounded, right? So we have to discuss both the cases. For both the cases, we are going to show that this capital F is continuous. Okay, let's take the first case, if f is bounded. If it is bounded on closed interval AB, then there exists a positive real number m such that mod of ft dt is less than equal to capital M for all t belonging to the closed interval AB. This is the definition for the boundedness of the function. So therefore, if we choose delta to be equal to, we choose this later on, right? So mod of x minus c less than delta implies mod of f of x minus f of c. We need this to be strictly less than epsilon for continuity. Now this is what? This is less than equal to this right hand side. So writing this to be less than equal to the integration from c to x mod of ft dt. And because the function is bounded, So I'm using this now, that mod of ft is less than equal to m. So writing this further, that this is less than equal to m with this integration from c to x. Integrating this with respect to t, we get m into t with limits from c to x. So this is m, putting the upper limit, it is x minus c, and x minus c is strictly less than delta. So this is strictly less than m into delta. Now I need to choose such a delta such that this m delta becomes epsilon. So I am taking this delta to be epsilon by this positive number m. So now write here that we have choose delta to be epsilon divided by capital M. So this is m into delta is epsilon divided by capital M. So m cancelled out with this m and we get this to be as epsilon. So we have found that mod of f of x minus f of c, this is strictly less than epsilon following this inequality. Epsilon was arbitrary, therefore f is continuous on c. And also this c is arbitrary, right? C is belonging to the closed interval AB. So C is any real number belonging to this interval. So because C is arbitrary, so therefore f is continuous on complete closed interval AB. So we have shown that f is continuous on closed interval AB if f is bounded. Now the another case when f is not bounded, right? Now the second case, assume that f is not bounded. So for this we have to define the function f(n)x to be equal to fx. Its value is fx if fx is less than equal to n and its value is n otherwise. Please remember this. Now from this defined we can notice that each of this fnx, f1x, f2x, f3x. What is f1x? If fx is less than equal to 1, then it is fx. Otherwise this f1x is equal to 1. Similarly the f2x, f3x. Now each f and x is bounded, right? And also non-negative measurable function. Non-negative measurable function means this function can take only the values which are greater than equal to 0. It takes the values greater than or equal to 0, right? Those are non-negative measurable functions. Then each f and x is bounded and non-negative measurable function. Right? And also fn is tending to f at each point. It is tending to fx at each point. So we can also say from this that fnx is an increasing sequence. It is an increasing sequence of non-negative measurable bounded functions and bounded functions, right? Such that this fn is tending to f on closed interval AB. So now here I am going to use the monotone convergence theorem. What that theorem is? Let fn be an increasing sequence of non-negative measurable functions and let f equal to limit n tending to infinity on fn. Then the integration on f is equal to the limit n tends to infinity on the integration on fn. So we are already having f and x to be an increasing sequence of non-negative measurable and bounded functions, and also fn is tending to f. So from here, can I use this monotone convergence theorem and write that? From this result, we write limit n tending to infinity the integration on f n t dt, and the limits from a to b is equal to the integration on f t dt, the limits from a to b. So from this we can use the definition that therefore for given epsilon positive there exists a positive integer n. This is the sign for there exists, such that the mod of integration from a to b f n t dt minus the integration f t dt from a to b, this mod is strictly less than, I'm not writing epsilon but instead I'm writing epsilon by 2 for n greater than equal to that capital N, right? Now this result is true for n greater than equal to capital N. So can I write the same result for n equal to capital N? Yes, because n is greater than equal to n. It can be greater than n, strictly greater than capital N, or it can be equal to n. So I'm writing the next step for n equal to capital N. So this is mod of, this implies it is the mod of integration from a to b f capital N t dt minus the integration from a to b f t dt strictly less than epsilon by 2, and because it is a mod I can interchange the terms. The expression inside the mod is strictly less than epsilon by 2 and also strictly greater than minus epsilon by 2. Yes, so writing this, I'm taking the integration common from a to b ft minus f capital N t dt. This is strictly less than epsilon by 2. Yes, from this step we can write this. Now we want to choose the delta. If we choose delta, we choose this later on, right? Mod of x minus c less than delta implies the mod of f of x minus f of c. This mod is less than equal to, from the very start of the proof, this mod is less than equal to this integration. So using this result, this mod is less than equal to the integration from c to x mod of f t dt. So this is equal to the integration from c to x, and I'm going to add and subtract f and t, and here plus f and t, and writing here dt. Because it is the mod, so which can further be less than equal to the integration from c to x, I'm taking this two together. So this is ft minus f n t dt. This is the mod and this is dt plus the integration from c to x on f n t dt. Its mod is positive f n t, that's okay. Now can I write in the next step that this f n t is less than equal to capital N by the definition, because we have defined our fnx to be equal to fx if f is less than equal to n, otherwise it is equal to n. So for n equal to capital N, because capital N is a positive integer, there exists a positive integer capital N for which this inequality holds, right? So that is why this also holds true, right? So I'm using this in the next step. So this f and t is further less than equal to, writing the first integral as it is, plus the integration from 0 to x, instead of f and t, just write capital N dt. Also, this mod is less than epsilon by 2 from this definition. So writing this further, strictly less than epsilon by 2 plus, and integrating this, we get the integration to be t from c to x, that is x minus c if you put the values, and this x minus c is less than delta from here, right? So this is strictly less than epsilon by 2 plus n delta. Now we have to choose such a delta such that this n delta becomes epsilon by 2, because I need the epsilon when adding these two together. So let's choose delta to be equal to epsilon divided by 2 capital N. So here I have to write now, if we choose delta to be epsilon divided by 2 capital N, it is necessary to write. So writing here plus n and choosing delta to be epsilon divided by 2n. So this n cancelled out with this, and we get this to be equal to epsilon. So what we have got, that this implies we have started from here. The mod of f of x minus f of c is strictly less than epsilon. And because epsilon was arbitrary, so therefore capital F is continuous at C. So F is continuous at C. And also because C is belonging to the closed interval AB. Any point can belong to the closed interval AB, so C is also arbitrary. But C was also arbitrary. So therefore we can write now that f is continuous on the closed interval AB, right? So for both the cases, whether small f is bounded or not, we have shown that the capital F is continuous on closed interval AB. So one thing is proved. Remaining is to prove that this is of bounded variation. And when the function is of bounded variation, if I get that the total variation on closed interval AB depending upon f should be finite, right? This we need to show now. So the remaining third part to show that f is of bounded variation. So for that, let's suppose the subdivisions of closed interval AB, x0 less than x1 less than x2 up to so on equal to b. Let this be xk. So this be any subdivision of closed interval AB. Then the total variation t is equal to what? We know that it is a summation from I to k on the modulus of f of xi minus f of xi minus 1, right? And is equal to summation I going from 1 to k. What is f of xi? It is given that this fx is the integration from a to x ft dt. We have to use this. So fxi becomes the integration from a to x, but not x, xi. ft dt minus the integration from a to xi minus 1 ft dt. Writing the first integral as it is, because I need to change this sign. So for that I need to interchange the limits and the sign will be changed. Writing this integral to the first place and this to the second place. Now the first integration is from xi minus 1 to a, and then second is from a to xi, right? Integrands are same. So we can merge these two integrals to get, just sum up these two integrals and we get the mod of integration from xi minus 1 to xi ft dt. I hope it is very clear, right? And because it is your mod, it is further less than equal to the summation I going from 1 to k, the integration of modulus of f of t dt and the limits xi minus 1 to xi. So when putting the values of I equal to 1 up to k, you will be getting this complete to be equal to the integration from a to b mod of ft dt. Right? And now taking the supremum, what is on the left hand side? It is t. Taking the supremum over all possible subdivisions of closed interval AB, we get this t will be changed into capital T, right? So we get this capital T to be for the closed interval AB on capital F, this to be less than equal to the integration from a to b mod of ft dt. And because this mod of ft is non-negative integrable function, so integration on this mod is always finite. It is non-negative integrable function. So therefore we get the total variation on the closed interval AB is finite, and when the total variation over closed interval AB is finite for this capital F, we write that therefore F is of bounded variation on closed interval AB. So hence this lemma is proved. Okay, thank you. Stay blessed.